Okay, so some of this will be familiar to you, girls. And some of it, as I said, we're putting a higher twist on it. Okay, so the theory behind it, you should be familiar with from National 5, but then we're going to look a little bit more at how we can adapt this to sort of higher physics. So, projectile motion. So we know that we can split the projectile motion into two different motions. We can split it into horizontal motion and vertical motion. And we also know that the vertical motion is acceleration due to gravity. So if you drop a ball, if you project a ball, it moves down slightly further each time because it's increasing the rate of drop, so the acceleration. And horizontally, it's constant speeds. So it travels the same distance every second, okay? So the vertical motion of the projected ball and the free-falling ball are in step all the way down. They're both accelerating downwards at 9.8 meters per second squared. The horizontal distances between the images of the projected ball remain the same. It's traveling at a constant speed horizontally. And if you think back to National 5, the equation you use for horizontal, you use your distance is speed times time, because it's just constant speed. Whereas vertically, you use in National 5 your acceleration equation, which was v minus u over t. We now look at it as v equals u plus at because it's one of our Suvat equations. We can also use other Suvat equations now. So if you think about when you did it in National 5, you ended up drawing graphs and then finding the area under the graph and all that kind of kerfuffle. You don't need to do that anymore because you use your Suvat equations. So actually it's a bit nicer than having to do area under the graph. So the motion of any projectile can be treated as two independent motions. The horizontal motion is constant speed. So if you had a speed time graph for horizontal speed versus time, you just have a horizontal line because it's constant speed. The vertical motion, however, is constant acceleration. So it's increasing vertical speeds at the same rate each, so same amount every time. So you would end up with a diagonal line like that. So into the horizontal motion, there are no unbalanced forces acting in this direction. We ignore air resistance. By Newton's first law, the projectile will keep moving at a constant speed horizontally. And vertical motion, due to the force of gravity, the projectile experiences an unbalanced force pulling it downwards, its weight, and its downwards acceleration will equal g. So in National 5 physics, we examine the situation where an object was projected horizontally. So in National 5, it was always projected horizontally. So girls, so the initial vertical speed was always 0 at National 5. Okay, so for example, a cannonball is fired from the edge of the ramparts of a castle. The ball is projected horizontally with a speed of 30 meters per second, and it hits the ground 87 meters from the base of the ramparts. So, first of all, on the diagram above, sketch the path taken by the cannonball. So it's projected horizontally, and then it also hit the ground like that. And we're told it travels 87 meters horizontally. And it's projected horizontally 30 meters per second. So, for part B, calculate the time of flight of the cannonball. So for this one, we're just looking at the horizontal speed. We know the horizontal speed is constant, so it's going to be 30 meters per second all along. We know the horizontal distance, so we're just going to use distance is speed times time. Because it's horizontal, the speed is constant. So the distance, 87. The speed is 30. And we want to find the time. So the time is going to be 87 divided by 30, which comes to 2.9 seconds. Okay, nothing new there. Because it's projected horizontally, what's the initial vertical speed? 0, yeah. And calculate the height of the ramparts of the castle. So we want to know what vertical distance it travels. So we would, whereas in National 5 you would have to do the speed time graph, find the area under the speed time graph, that's the distance travels. Now we have other tools at our disposal. So what do? We write down SUVAC. So S is what we want to find. U is the initial vertical speed, so 0. V, we don't have a final vertical speed. The acceleration, well, let's say what's used downwards to be positive because it's moving down the way. Acceleration is going to be 9.8. And the time we worked out to be 2.9 seconds. So we can rack our brains thinking back to our SUVAC equations. S equals ut plus half at squared. So S equals 0 plus half times 9.8 times 2.9 squared. So S should come to 41.2 meters. So absolutely nothing new there. We've used the SUVAC equation instead of using area under the graph. Some of you might have used some SUVAC equations in the past for this anyway, but technically it wasn't National 5. So if you are rusty and you're unfamiliar with some of the projectiles of National 5, you'll need to go home and just remind yourself of some of the National 5 projectiles, because we're going to move on and look at the higher versions of them. So if you've written that down, by all means, just start reading through the next page, because you'll see what the difference is. Okay, so projectiles in higher physics. The difference between projectiles in National 5 and in higher is that in higher physics they are projected at an angle, girls. So they're not projected horizontally anymore, so the vertical speed will not be 0 anymore. So we have to work out what the vertical and horizontal speeds are. So same kind of thing happens though. Vertically, there's an acceleration due to gravity. Horizontally, the horizontal speed is constant. Okay, but we have to first of all work out what those speeds would be. So the main change in higher physics is that we now consider the much more common scenario where projectiles are not launched horizontally or vertically, but somewhere in between. An analysis of these projectiles involves calculating components of the initial velocity vector before we can consider using any formula or forming any calculation. So remember when we had forces at an angle and we had to find the components of the forces? Same kind of thing here. We have to find the components of the vector, the velocity. So the initial velocity of the object being projected will usually be resolved into a component of that velocity in the horizontal direction and a component of that velocity in the vertical direction. So we normally consider the angle of launch as being an angle theta above the horizontal, so like that diagram there. If we make a right-angled triangle from the initial velocity vector, and then the launch velocity would be the hypotenuse of that triangle. So basically what that's saying is our launch velocity, so this is, we might say something's launched at 20 meters per second at an angle of 30. So that would be your 20 meters per second, and that would be your 30. But that's not useful for us in projectiles. What we need is we need the horizontal component and we need the vertical component. So we draw this triangle here. We've got a right angle triangle. We'll call that our x and that our y. So to find the x component of that velocity, we just use SOHCAHTOA. Okay? So to find Vx, we'd use cosine. So cosine theta is adjacent over hypotenuse. So cosine theta would be Vx over the speed, the speed that we're told it's traveling, it's launched at. So Vx would be V cos theta. And if you understood the cheat method that I taught you when we were doing the forces, basically this velocity has gone through the angle, so it's cos theta. If you don't understand that, just ignore what I just said. Okay, and remember this horizontal velocity would be constant throughout the motion because it's the horizontal component. So that's what that second paragraph says there. In order to calculate how far per second the projectile is moving horizontally, we'd need to find the size of the adjacent side of this vector triangle. And if we make the assumption that we can ignore air resistance, then there's no force acting on the projectile in the horizontal direction. So this horizontal speed will be constant for as long as the projectile remains in the air. So similarly, to find Vy, got the same triangle again. To find Vy, we'd use the sine. So sine theta is opposite over hypotenuse. So sine theta is Vy over the launch velocity. So Vy is the launch velocity times y sine theta. That would not be constant, that's just your initial velocity. Okay. So we can use trigonometry to calculate how fast the object is initially moving in the vertical direction. As soon as the projectile is launched, its weight will begin to pull it back down to Earth, and it will accelerate downwards at a constant rate of 9.8 meters per second squared, assuming the air resistance is ignored. It's important to note that if the projectile is launched with an initial velocity upwards, the vertical acceleration will be in the opposite direction, and careful use of a sign convention is required. Remember, acceleration always acts down the way, so if you're using upwards to be positive, your acceleration will be negative. So you just need to remember that as well. So it's another thing to keep on top of. I'll leave that for a little bit. If you've written that, read through the next example and just have a think about it. Okay. So, example 2 is a bit of a weird question. It's not really asking you anything specifically. It's just saying write down everything you can find out. So, the operator in charge of the cannon on the ramparts from the castle, from example 1, tilts the barrel so that it's 15 degrees above the horizontal. So it's shot at an angle now. The cannonball leaves the barrel with the same speed. So the speed was 30 meters per second. So, sketch the new path taken by the projectile. So, basically what will happen is it will go up first and then up down. So, it's shot off at 30 meters per second at an angle of 15 to the horizontal. Okay, so that's basically zoomed in to there because I can't really fit it. So, do you think it will land closer to the ramparts, at the same point, or further away from the ramparts? Anyone have any ideas? Closer? Well, we'll see because we're going to work it out. Okay. So, assuming the height of the ramparts has not changed, quantify everything you can about the projectile at the instant it lands. Okay, so the height was 41.2 meters. So that says it hasn't changed. So we've still got 41.2 meters there. So basically what it wants us to do is fill in all of this information. Right, so we don't know what distance horizontally it travels. Some of us, we think that it probably would be shorter, but we don't know. Speed, the horizontal speed. Now the horizontal speed is not 30, it's going to be 30 cos 15, because it's the horizontal component of the speed. So 30 cos 15, and I know that the mathematicians amongst us will want to leave it like that, but we have to work it out. In physics, they won't give you the mark if you just leave it as a cosine. So that comes to 29.0 meters per second. So you need to put it into your calculator. Be careful with your radians and your degrees. Oh, you don't need to. I'm just being. Okay. Guys, what else do we know? We don't know the time it takes either, and we can't work that out unless we've got the distance. So we'll just leave that aside for now. Vertical. Right. Vertically, it's being shot upwards first, so I'm going to take up to be positive. Okay, so our vertical distance, which is the height of the ramparts, is actually going to be, because it's down the way, so it's minus 41.2 meters. Our initial vertical speed is no longer 0, it's going to be 30 sine 15. And again, you need to put that into your calculator, it comes to 7.76 meters per second. Acceleration, we know, is due to gravity, so negative 9.8 meters per second squared, because if we used upwards to be positive. We don't know anything about v yet, and we don't know anything about t yet, and we need t to go ahead and find the horizontal distance. So what can we do? Well, we can use a couple of Suvat equations to work out our vertical information. So to find v without t, we could use v squared equals u squared plus 2af. So v squared is 7.76 squared plus 2 times minus 9.8 times minus 41.2. So v squared comes to 867.8, blah, blah, blah. So v, you leave that in your calculator, just square root it. V comes to plus or minus 29.5 meters per second. This is just for sort of like your notes for completionists. But we know that the vertical speed is down in the down direction, just because we know that's what's going to happen. So it will be negative. Yeah. But the reason that I put plus or minus there is because when you square root something, you technically don't know whether it's a plus or a minus, but you can then see from your, common sense that it would be negative 29.5. So we've got the v, negative 29.5 meters per second. Then to find t, I've just put v and c there. To find t, v equals u plus 80. You could use a couple of different equations for that. So minus 29.5 equals 7.76 plus minus 9.8 times by time. So the time comes to 3.8 seconds. Yeah. If you look at the diagram, it's going up and then down, and we've taken upwards to be positive, so it's going to be negative. It could be positive or negative from your answer, you don't know, but you can just tell from the motion. Apologies for that noise. Don't know what is happening out there. Right, now we know the time, we can now use that in our horizontal motion. So, because the time is obviously going to be the same. So define the horizontal distance, horizontal speed times horizontal time. So 29.0 times by 3.8, which comes to 110 meters. In example 1, the distance was 87. Example 2, 110. Okay. Have a read through the next example. Even have a go at it if you want to. You'll never get asked a question like this where it just says fill in loads of different information. It will be more specific than that. It's in case you needed extra space. Depends how big your writing is. Yeah, you never know. Am I okay to move on from this? Is anyone still writing this? We all good? Okay. Last examples of class, then you guys have got plenty of practice to do. So, example 3. A long jumper devises a method for estimating the horizontal component of his velocity during a jump. His method involves first finding out how far he can jump vertically, I think, rather than Beth can jump. So he finds that the maximum height he can jump is 0.86 meters. Show that his initial vertical velocity is 4.1 meters per second. Okay, so again, you've got quite a lot of space for this, so you can spread out, you don't need to squish it all in. So we'll do part 1 down here. So we've got maximum height, so we're going to look at our Subat values. And he's jumping up, so I'm going to use upwards to be positive. So maximum height, 0.86 meters. What do we know about the speed at the maximum height? 0, yep. It's always something you need to have in the back of your head because it won't always tell you that. Initial vertical speed is what we want to find out. And acceleration is negative 9.8. That's down the way and we're taking upwards to be positive. Don't know anything about time. So the equation we're going to use is v squared equals u squared plus 2as. So 0 squared equals u squared plus 2 times negative 9.8 times by the s, which is 0.86. So u squared comes to 16.8 something, so u comes to 4.1 meters per second. Okay, so he now assumes that when he's long jumping, the initial vertical component of his velocity at takeoff is 4.1 meters per second. So it's assuming that's the vertical part of his velocity at takeoff. The length of his long jump is 7.8 meters. Calculate the value he should obtain for the horizontal component of his velocity. Okay, so what do we know? So let's just write down everything we know first of all. So we've got horizontal motion and we've got vertical motion. So horizontally, we know the distance is 7.8 meters. We want to know the initial horizontal speed, and we don't know the time. Vertically, so we know that his initial vertical speed is 4.1 because he's assuming that it's 4.1. We can look at the acceleration we know is going to be minus 9.8. And what I would do is, if in doubt, we don't really have much else information there, well, let's look at halfway. So okay. So for halfway, let's find the time. We need the time, don't we, to then work out what that velocity is. Yeah, it's not a straight line. We're assuming he's a projectile. Yeah, we're modelling him as a perfect projectile. Okay, yeah, you're right. There would be other things as well. We don't know it is going to be at high this time. Probably will be, but we don't know it. So we want to find out the horizontal component of his velocity. So initial horizontal speed. Right, so finding the time, let's just use v equals u plus at. We take upwards to be positive. So 0 equals 4.1 plus negative 9.8 times by time. So time for halfway is 0.42 seconds. So we're assuming it's symmetrical, so total time so now we've got that, we can put it into our horizontal motion to find the initial horizontal speed. Okay, guys? So we're going to use horizontal motion, distance is speed times time. We know the distance is 7.8. We want to find the horizontal speed, and the time is 0.84. So the horizontal speed of the horizontal component of the initial speed will be 9.3 meters per second. You get it right? Oh, okay. Right. Are you happy with you? We want to find the value for the horizontal component of his velocity at the start or at the end. I'll let Becca explain it to you, and then if you're still unsure, let me know. Right. So I want to pause there, and I want you guys to have a go at some of these. So pages 3 to 9 of your question booklets, please.